Gravity is one of the most fundamental forces in nature. It is responsible for keeping planets in orbit, holding objects on the ground, and maintaining the large-scale structure of the universe. From the motion of galaxies to the simple act of an object falling to Earth, gravity plays a central role in shaping physical reality. The scientific understanding of gravity was first clearly described by Isaac Newton in the 17th century. His work marked a turning point in physics, as he proposed that the same force responsible for objects falling on Earth also governs the motion of celestial bodies. This unified explanation allowed scientists to understand both terrestrial and astronomical phenomena under a single principle. Newton's idea was based on the observation that every object in the universe exerts an attractive influence on every other object. This means that all matter, regardless of size, participates in gravitational interaction. Although the force between small objects is extremely weak, it becomes significant when large masses such as planets and stars are involved. Gravity depends mainly on two key factors, mass and distance. Objects with greater mass produce a stronger gravitational effect, which is why planets, stars, and galaxies have such powerful influence. On the other hand, as the distance between objects increases, the strength of gravity decreases rapidly. This relationship explains why gravitational effects are strong at short distances but become weaker over vast regions of space. One of the most important characteristics of gravity is that it is always attractive in nature. Unlike some other forces in physics, gravity does not repel, it only pulls objects toward each other. It acts along the line joining the centers of two masses and influences motion in a predictable way. Another key feature of gravity is its infinite range. It extends across the entire universe, meaning that every object, no matter how far apart, exerts some gravitational influence on others. Even though this force weakens with distance, it never truly becomes zero. Despite being the weakest among the fundamental forces of nature, gravity dominates at large scales. This is because it is always attractive and accumulates over massive bodies. As a result, it becomes the primary force governing the structure and behavior of astronomical systems. Gravity is responsible for many observable phenomena in our daily lives and in the universe. It causes objects to fall toward the Earth, giving them weight and direction of motion. Without gravity, there would be no concept of up or down, and objects would not remain attached to the Earth's surface. It also plays a crucial role in maintaining the motion of celestial bodies. The Moon remains in orbit around the Earth due to gravitational attraction, and the Earth, along with other planets, orbits the Sun for the same reason. These orbital motions are stable because gravity continuously provides the necessary force to keep these bodies in their paths. In addition, gravity is responsible for ocean tides. The gravitational pull of the Moon, along with the Sun, causes periodic rising and falling of sea levels on Earth. This interaction demonstrates how gravity operates not only on solid objects but also on large bodies of fluid. On Earth, gravity produces a constant downward acceleration, which determines how objects move when they are released from rest. This acceleration is nearly uniform across the Earth's surface, allowing scientists to study motion with a high degree of accuracy. It also defines the weight of objects, which is the force exerted by gravity on a given mass. At much larger scales, gravity becomes the force that shapes the entire universe. It governs the formation of stars, galaxies, and clusters of galaxies. Over time, gravitational attraction causes matter to come together, forming complex structures that define the observable universe. Without gravity, matter would remain scattered, and stars and planets would not form. There would be no organized systems, and the universe as we know it would not exist. Thus, gravity is essential not only for motion but also for the existence of structure itself. In the 20th century, Albert Einstein introduced a new understanding of gravity through his theory of relativity. According to this theory, gravity is not simply a force acting at a distance. Instead, it is the result of the curvature of spacetime caused by mass and energy. This means that massive objects such as planets and stars distort the space around them, and other objects move within this curved geometry. This concept provides a deeper explanation of gravitational phenomena, especially in extreme conditions such as near black holes or very massive stars. Einstein's theory also explains effects that cannot be fully described by Newton's model, such as the bending of light around massive objects and the behavior of time in strong gravitational fields. However, for most everyday applications and calculations, Newton's law of gravity remains highly accurate and widely used. In conclusion, gravity is a universal force that governs motion and interaction at all scales. From small objects on Earth to the largest structures in the universe, it plays a critical role in shaping physical reality. Understanding gravity is essential for studying physics, astronomy, and the fundamental nature of the universe.